Hello and welcome back to your Chem 4 lecture. We are wrapping up Chapter 7 today, Section 7.7 through 7.9 in this lecture. And in this lecture, we're going to talk about what we call stoichiometry, which sounds like a really scary thing, but it's really just mole relationships and stuff that you probably already know, but we're going to put some math behind it so that we fully understand it. Basically, what we're going to do is we're going to combine what we know about the mole with what we know about the conservation of mass to understand how reactions occur and how much product we can expect from a given amount of reactant. So here we go. So starting here, this is just a diagram here. This has 2 moles of iron plus 3 moles of sulfur reacting to form 1 mole of iron 3 sulfide. I'm just kind of showing you the relationship here. And basically the idea is if you add this mass and all of this is used up, and you add this mass and all of this is used up, then you should get the mass of the product. That's what we talked about when we talked about the law of conservation of mass in a chemical reaction. So remember, the law of conservation of mass says that in an ordinary chemical reaction, that is to say, a non-nuclear reaction, so all the ones that we're going to talk about, matter is neither created nor destroyed. There's no change in total mass. And so the mass of the products is equal to the mass of the reactants. That's how we've said it before. In practical terms, what that means for chemistry is that you end up with the same number of moles of each type of atom in the reactants as in the products. Again, here's another example. If you take 2 moles of silver here, weighing 215.8 grams, and combine it with 1 mole of sulfur, weighing 32.1 grams, and you react them in a chemical reaction, you end up with 1 mole of silver sulfide, which is also 247.9 grams. So note, there was no loss of mass, and there's no loss of atoms either in this reaction. And in a balanced reaction, we notice we have 2 times the number of silver atoms reacting for each sulfur atom, which makes sense because when we look at silver sulfide has 2 silver atoms for every 1 sulfur atom. Okay, so here are the types of information that we can get from a balanced chemical equation like this. Well, we talk about it often in terms of the number of atoms. So it's easy to say, okay, 2 silver atoms react with 1 sulfur atom to produce 1 formula unit of silver sulfide. Now, you could also say that just as easily, you could have 2 moles of silver atoms reacting with 1 mole of sulfur atoms to produce 1 mole of silver sulfide. Yeah, and you can multiply this as needed too, right? So it says 200 silver atoms versus 2 silver atoms plus 100 sulfur atoms gives 100 silver sulfide formula units. Totally fine. But note here in the balanced chemical equation, if we do the equation right, we have a balanced conservation of mass from the reactants to the products. Okay, so now looking at this one again from the opening slide. We can read this reaction as saying 2 moles of iron react with 3 moles of sulfur to produce 1 mole of iron 3 sulfide. And that's just the same as saying 2 atoms of iron react with 3 atoms of sulfur to produce 1 formula unit of iron 3 sulfide. Okay, now in this reaction, we have several what we call mole-mole factors as a way of being able to convert from the number of moles of one of them to the number of moles of the other. For example, we know that for every 3 moles of sulfur that react, we need 2 moles of iron. Well, that gives us a conversion factor, right? We know we need 2 moles of iron for every 3 moles of sulfur. And the opposite is true as well, if we're thinking about it in terms of iron. If we have a certain amount of iron and we want to know how much sulfur we need, well, we know that we need 3 moles of sulfur for every 2 moles of iron. So in that way, we can convert from the number of moles of iron we have to the number of moles of sulfur that we need. Now, let's say that we want to calculate the amount of product that we would make. Well, we know that for every 2 moles of iron, we produce 1 mole of iron 3 sulfide. So that's a way that we can predict from a given amount of iron, the amount of product that we would make. On the counterpart, we could also think, oh, I want to make 2 moles of iron 3 sulfide. How many moles of iron do It's a very practical consideration when you're working in lab. You always think, oh, this is the amount I need to make. How much of the starting material, the reactants, do I need to use to do that? Well, you know that you need 2 moles of iron for every 1 mole of iron 3 sulfide. And the same is true for sulfur. You can do both of those equations for sulfur. These are all called mole-mole factors. And these ratios are extremely useful, and we're going to be using them basically from now on throughout the semester. Okay, so let's go ahead and consider the following equation. This isn't one of your sample exercises. We're just going to kind of walk it through here together, and then we'll move into sample exercises in a little bit. Okay, so consider the following equation. We have 3 hydrogen with 1 nitrogen reacts to form 2 ammonia, that's NH3, as a gas. What is the mole-mole factor that you would use for hydrogen and nitrogen from this? Is it 1, 3 moles of nitrogen for 1 mole of hydrogen? Is it 2, 1 mole of nitrogen for 3 moles of per 3 moles of hydrogen? Or 3, is it 1 mole of nitrogen per 2 moles of hydrogen? Again, what's the mole-mole ratio or mole-mole factor that you would use here? And then B, a mole-mole factor for NH3 and H2 is, is it 1 mole of H2 for every 2 moles of NH3? Or is it 2 moles of NH3 per 3 moles of H2? Or is it 3 moles of N2 per 2 moles of NH3? Well, looking at the balanced equation here, we know that there are 3 moles of hydrogen that react with 1 mole of nitrogen. So that would give us the correct answer here being number 2, where there's 1 mole of nitrogen reacting for every 3 moles of hydrogen. Then down here it says the mole-mole factor for NH3 and NH2. Well, we produce 2 moles of NH3 for every 3 moles of H2 that we use. So 2 again looks like the correct answer to me. So that's how you can identify a mole-mole factor. And then, of course, this mole-mole factor can be used as the conversion factor. And that's what we're going to do in the next. In fact, a lot of these calculations that we're going to do the rest of the semester involve mole factors. So we want to be able to use them and get very good at them very quickly. So a type of problem that I could ask, for example, on the test, this is kind of a basic one, but we'll kind of build it up. We can ask how many moles of iron 3 oxide can form from 6.0 moles of oxygen. Given an equation that we could balance, you have the balanced equation as 4 moles of iron react with 3 moles of oxygen to produce 2 moles of iron 3 oxide. Well, what's our relationship here? We know, starting from 6.0 moles of oxygen, for every 3 moles of oxygen that react, 2 moles of iron 3 oxide are formed. So our mole ratio would be 2 moles of iron 3 oxide per 3 moles of oxygen. So then we're ready to set up our conversion factor. So it's 6.0 moles of oxygen, excuse me, here. And then the conversion factor is 2 moles of iron 3 oxide for every 3 moles of O2. Moles of O2 cancel out, and that gives us our answer to 2 significant figures, 4.0 moles of iron 3 oxide. And here, I think I can fix this right now. I just noticed this should be, I have to actually edit that, hold on. So I'll edit that later, but this should be 6.0 over here. And then because this is 6.0, that's 2 significant figures. Then 2 and 3 here, these are exact numbers, right? You balance this equation according to conservation of mass, you have to have exact numbers here. So the answer is going to be 2 significant figures as well. Okay, so here we go. Now we're ready for sample exercise number 13. Given this same equation, how many moles of iron are needed for the reaction of 12.0 moles of oxygen gas? Note that oxygen gas is O2. So go ahead, give it a shot. Pause the video here. Try to use the correct mole ratio, mole factor, and then when you come back, we'll walk through the problem. Let's go ahead, pause. Okay, I'm going to assume that you're back now. So the question again, how many moles of iron are needed for the reaction of 12.0 moles of oxygen? Well, we know that 4 moles of iron react with 3 moles of oxygen to produce 2 moles of iron 3 oxide. So the relationship here is going to be 4 moles of iron for every 3 moles of oxygen. Okay, so the mole-mole factor should be 4 to 3. 4 moles Fe per 3 moles O2. Now we're ready to convert 12.0 moles times 4 moles iron divided by 3 moles oxygen, giving us 16.0 moles of iron. Okay, so that's good enough, right? But the truth is, when we're working in the lab or anywhere really, we don't measure compounds in terms of the number of moles. Instead, we measure the mass usually, especially in lab. We have the mass or some other equivalent way that we can measure that number of moles. So what we're going to do next is we're going to combine these mole factor calculations with molar mass calculations. And from that, we'll be able to determine, given a certain amount of a substance A, how much of substance B is needed or substance B is produced. So this is the way that we do that, basically. If we first convert the mass of substance A to moles using the molar mass of A, then convert the moles of substance A to moles of substance B using the mole ratio from the balanced equation, and then 3, convert the moles of substance B to grams using the molar mass again, this time of substance B. This is going to be something that we do just, this is the type of calculation that you should be able to do in your sleep by the end of this chapter. So this is something that's going to take a lot of practice, but between the lecture now and the homework, hopefully you'll get the feeling for it. We'll also have a stoichiometry worksheet later on. Okay, so let me tell you, let me give you an example calculation that we'll put in our notes, and then we'll do the sample exercise calculation. So here we go. Suppose we want to determine the mass in grams of ammonia that can be produced from 32 grams of nitrogen in the following equation. We have nitrogen plus 3 hydrogen react to form 2 ammonia. So 1 mole of nitrogen plus 3 moles of hydrogen react to form 2 moles of ammonia. Okay, now we're given the fact that we have 32 grams of nitrogen, and we need grams of ammonia. So how can we do that? Well, this is the mass-mass conversion we were talking about before. Starting from grams of nitrogen, we can use the molar mass of nitrogen to determine the number of moles. Once we have the number of moles of nitrogen, then we're ready to use the mole factor to get the moles of ammonia that would be produced from that amount of nitrogen. Finally, we use the molar mass of ammonia to convert to grams of ammonia, and that will be our answer. And now we know how to do each of these things. The molar mass of nitrogen, of course, is just 2 times the molar mass of nitrogen on the periodic table. The mole-mole ratio for nitrogen to ammonia, well, 1 mole of nitrogen produces 2 moles of ammonia. So it's 2 moles of ammonia per 1 mole of nitrogen. And then finally, the molar mass of ammonia is going to be 1 times the molar mass of nitrogen plus 3 times the molar mass of hydrogen. Okay, so let's go ahead and find those out. For nitrogen, the molar mass is 28.02 grams per mole. For ammonia, it's 17.04 grams per mole. And then finally, we already said this here, but our mole conversion is going to be 2 moles of ammonia for every 1 mole of nitrogen. Now we're ready to set up our problem. So we start from 32 grams of nitrogen. There's 1 mole of nitrogen per 28.02 grams of nitrogen. Grams of nitrogen cancel out. Next up, our mole ratio. Well, there's 2 moles of ammonia that are produced for every 1 mole of nitrogen. Moles of nitrogen cancel out. Finally, we need the grams of ammonia. So we know that there's 17.03 grams of ammonia for every 1 mole of ammonia. Moles cancel out again. Solve it here. We started with 2 significant figures. Each of our molar masses had 4 significant figures. The answer, then we know the 2 significant figures, and that is 39 grams. Okay, so here we go. So now we're going to change the rules here a little bit for sample exercise 14. Rather than asking how much you're going to produce, instead, we're flipping it. I'm asking you, how much do we need? So the question here is, how many grams of oxygen are needed to produce 45.8 grams of iron 3 oxide in the following reaction? We have the balanced equation, 4 moles of iron react with 3 moles of oxygen to produce 2 moles of iron 3 oxide. And you have 3 possibilities here, 38.4 grams, 13.8 grams, or 1.38 grams. So go ahead, pause the video now, work this out, and then when you come back, we'll work through the answer. So go ahead, pause. Okay, I'm going to assume that you're back. Okay, so again, let's look at the question. How many grams of oxygen are needed to produce 45.8 grams of iron 3 oxide. Well, here, this time we're working back. We have the amount that we produced. So the question is, how much do we need? So we need to convert from the grams of iron 3 oxide to the moles of iron 3 oxide, then from the moles of iron 3 oxide to the moles of oxygen, and then finally from the moles of oxygen to the grams of oxygen. So this is our plan. Grams of iron 3 oxide converted to moles of iron 3 oxide, moles of iron 3 oxide converted to moles of oxygen, and then finally moles of oxygen converted to grams of oxygen. Well, we just find our conversion factors from here. We know that there's 1 mole of iron 3 oxide for 159.70 grams of iron 3 oxide. Next up, we know that we produce, oh, this is the wrong one here. Sorry about that. Looking at it here now, we know that we use 3 moles of oxygen for every 2 moles of iron 3 oxide. So it's a 3-to-2 ratio there. And then finally, we know that oxygen has a molar mass of 32.00 grams. Okay, so that gives us our final part here. So it's 45.8 grams of iron 3 oxide times 1 mole iron 3 oxide divided by the molar mass, 159.70 grams of iron 3 oxide. Next up, we have 3 moles of oxygen per 2 moles of iron 3 oxide. Moles of iron 3 oxide cancel out. And then finally, 32.00 grams of oxygen per 1 mole of oxygen, giving us our final answer here, 13.8 grams of oxygen. We started out with 3 significant figures. Our atomic masses, our molar masses were 5 and 4 significant figures, meaning our answer we know to 3 significant figures. The answer is B. Okay, that brings us to sample exercise number 15. Go ahead, pause the video one more time here and try to answer that the reaction between hydrogen and oxygen produces 13.1 grams of water. How many grams of oxygen reacted? So go ahead, pause the video here and give it a shot. And when we come back, we will go ahead and look at how we got the answer. So pause. And we're back. Let's go ahead and think it through. So this is a lot like the last problem. Of course, different products and reactants, but we made 13.1 grams of water, and we're asking how many grams of oxygen reacted. So all we need to do is take the grams of water to moles of water. Then we know that for every 2 moles of water that were produced, 1 mole of oxygen reacted. And then 1 mole of oxygen, we can convert it to grams using 32.00 grams per mole. So let's go ahead and look at our answer here. It's 13.1 grams of water times 1 mole of water per 18.02 grams of water. And then our mole factor is 1 mole of oxygen per 2 moles of water. And then finally, we have 32.00 grams of oxygen per 1 mole of oxygen, giving us our final answer of 11.6 grams of oxygen. Okay, so those are the examples of like mass-mass conversions that we can do. Now, the other part of chemistry that we need to keep in mind is how energy interacts with chemical reactions. This here is an example of a sample reaction called the thermite reaction that sparks up very hot. And this has been used to weld railroad tracks together. So that's a way to get the iron really hot in railroad tracks and then actually melt it together. Okay, so what do we know about chemical reactions? In order for a chemical reaction to occur, we've been writing these formulae, right? So we understand that molecules can interact with one another in such a way that they then change the arrangement of the atoms. But how does that actually happen? What actually has to happen for that to occur? Well, there's three things that need to be satisfied in order for a reaction to occur. Step one is the reactants that you have to collide. They literally physically, the molecules have to hit each other. Step two, orientation has to be satisfied. In other words, the atoms or molecules have to hit each other in such a way that they will break their old bonds and form the new bonds that the reaction predicts. And then finally, they have to hit each other with enough energy in order for these bonds to break and the new bonds to form. So in other words, if 2 molecules hit each other rather lazily, then nothing's going to occur. This is the case for example, hydrogen and oxygen. Hydrogen combusts with oxygen spontaneously. However, if you just have hydrogen at room temperature and oxygen at room temperature, they can mix freely. It's not really a problem. The problem is when you have a spark. Now, a spark represents heat, and heat represents the ability of molecules to move faster and collide with more energy. So that provides the energy of activation, and then all of a sudden, your hydrogen can either catch on fire if you're lucky, or explode if you have the wrong mix of hydrogen and oxygen. Okay, so this is what's called the energy of activation. If the two molecules hit each other rather lazily, without this energy of activation, still no reaction will occur. So you have to satisfy all three of these things. You have to have a collision, the molecules have to be in the proper orientation, and they have to have enough energy to actually have the reaction occur. Okay, now this here is what we call an energy diagram. Energy diagrams are a little advanced, but they're an extremely useful way to think of chemistry. So that's why we introduce them even here in Chem 4. It's because they're just the most useful way to understand what's actually going on in chemistry. So this is what we have here. So think of like, you can think of just like a table, okay? And this table, no, not a table. Let's think about like a hilly area, so like a hilly park. And this hilly park has, areas that are kind of valleys locally, and then there's, of course, ridges, and then lower parts as well. Now, if you have a ball that's in a relatively high ridge, or sorry, not ridge, if it's in a relatively high valley, that ball is going to be happy being at the bottom of whatever that local valley is. However, if you were to kick the ball from this valley here up the hill and it hits here, well, which way is it going to go? If you give it enough energy, it'll go over this hump and then all the way down to the bottom of this valley. So this is an example of having this ball up here and then having it down here. Up here, it had more potential energy. Then down here, that potential energy is gone because it's closer to the center of the Earth. There's gravity is pulling it. It is closer to the center of the Earth, so there's less gravitational potential energy, is what we would say. The same thing is true with chemicals. Basically, every chemical has some potential energy, and that potential energy can be released in a chemical reaction where the products have less chemical potential energy. In this case, where the energy of the reactants is higher than the energy of the products, heat is released, and we call this an exothermic reaction. Note the way this looks here. We have an activation energy here. This activation energy represents the amount of energy that it takes to basically break the bonds that we have in the reactants and form the bonds that we have in the products. In an exothermic reaction, heat is considered a product. So you can write the heat down here as a product. The other type of reaction is called an endothermic reaction. The way that you can remember this is think exoskeleton versus endoskeleton. As humans, we have an endoskeleton, the skeletons inside of our body. But bugs, for example, have an exoskeleton. That means there's skeletons on the outside of their body. So exo means outside, thermic means heat. So outside heat or releasing heat. Endothermic, inside heat or bringing heat inside. So heat gets absorbed by the reactants in an endothermic reaction and produces a product that has higher energy. Note here the activation energy is significantly higher because now you have to think of it, again, kicking the ball. You have to kick the ball all the way up this hill in order to get over here to where the products are. Whereas previously, you just had a small distance to kick it, and then the ball is going to roll down the other side of the hill. Now, in this case, heat is a reactant. So you have to add in heat to get the reaction to actually occur. Good example is the reaction of nitrogen and oxygen gas. Fortunately, this is a very difficult reaction to occur since nitrogen and oxygen are everywhere. If this happened a lot, we would be poisoned constantly by nitrogen monoxide. Okay, so given that information, identify each of the following reactions as exothermic or endothermic. This is the type of problem that you'll see on the test for sure. And basically, all you have to do is ask yourself, okay, is heat a reactant or a product? And that's going to tell you which one you have. So go ahead, pause the video, work out A, B, and C, and then when you come back, we'll look at the answers. So go ahead, pause. Okay, we're back. For A, there's 22 kilocalories as a product. So that's an indication that we have an exothermic reaction. For B, there's 133 kilocalories as a reactant. So that's an endothermic reaction. For C, it says heat. It just says heat is released as a product. Again, as a product, heat, that means it's exothermic. Okay. Now, that's not the only way. That's not the only thing that we have to understand. We also need to understand how we can increase the rates of a reaction. So the reaction rate is the speed at which a reactant is used up or the speed at which a product is formed. And the reaction rate always increases when the temperature rises. Now, the reason for that is because as the temperature rises, the motions of molecules increases, right? So a cold gas, for example, molecules are moving relatively slowly, bouncing, off the container, the walls of the container. As you heat it up, what you're really doing is you're increasing the speed at which those atoms are moving or the molecules are moving of the gas. So then all of a sudden, now when you have chemical reactants, what can happen is as you speed it up, they're going to hit each other more and they're going to hit each other with greater energy. So that's going to satisfy both the fact that you have more collisions, which are required, and collisions at higher energy, which is required. So more collisions that are between molecules that have the energy of activation. And you can also increase the reaction rate by increasing the concentration of reactants. The other way that you can increase the rate of reaction is using a catalyst. Now, we're not going to talk too much about this just yet, but basically all biological reactions are catalyzed through the use of enzymes, which are proteins in our bodies. Enzymes themselves are these, so when you think about life and I think about it from a chemical perspective, so trying to divorce yourself with your personal experience or how we feel about these things. Life is kind of like a series of chemical reactions. Again, from a chemistry perspective. I'm not saying that's from a spiritual perspective, just saying this is the chemistry perspective. We're like a sack of chemicals that's constantly undergoing these chemical reactions. And there's, many, many millions of chemical reactions occurring in our body each second. And each of these chemical reactions is catalyzed by the use of enzymes. So whether that's DNA synthesis, RNA synthesis, the making of proteins, then those proteins, being made to snip apart molecules and, harvest energy from food. These are just like a small subset of the reactions that have to occur in order for life to exist. So how do these enzymes actually work? Well, what they do is they basically, rather than having two molecules have to hit each other in the right orientation and with the right amount of energy, what an enzyme will do is it gives a pocket for reactant A and a pocket for reactant B that they really like to sit on, and then brings those two together and makes them react in such a way that then they leave and it does the reaction just in that one way. Now, these catalysts lower the energy of activation by, again, providing those pockets where those molecules want to be. And catalysts also don't get used up during a reaction. So it's then available to do it again for another thing. Okay, so how do you increase the reaction? Well, you could increase the temperature for an inorganic reaction. You could also increase concentration for an inorganic reaction. And then finally, if possible, you can add a catalyst, which just provides a way for the reaction to occur at a lower energy. Okay, so that brings us to sample exercise 17. And for this one, what I want you to do is tell me what is the effect of each of these on the rate of reaction? Does the rate of reaction increase, decrease, or no effect given all of this? So go ahead, pause the video, think through what we just talked about, and then we'll go over the answers together. Okay, so let's go ahead and do it. Hey, increasing temperature. Well, that's one that I literally told you Increasing the temperature increases the rate of reaction. So increasing temperature increases. Removing some of the reactants, well, that decreases the concentration of reactants. So that makes it less likely for the reaction to occur, so it's going to decrease it. Adding a catalyst increases the rate. Placing the reaction flask on ice decreases the temperature, so that decreases the rate of reaction. And then finally, if you increase the concentration of one of the reactants, that increases the rate as well. Okay, here we go. So indicate the effect of each factor listed on the rate of the following reaction as increases, decreases, or no change. We have a specific example. We've got 2 moles of carbon monoxide reacting with 1 mole of oxygen to produce 2 moles of carbon dioxide. Go ahead, pause the video, think it through, and then when you come back, we'll go through whether these increase, decrease, or no change. Let's go ahead, pause. Okay, and we're back. So raising the temperature, of course, increases the rate of the reaction. Adding oxygen, that's a reactant, so that's going to increase the rate of the reaction. Adding in a catalyst would increase the rate of the reaction. And then finally, lowering the temperature would decrease the rate of the reaction. Okay, that takes us through chapter 7. Believe it or not, you made it to the end. This was a long chapter for sure, just like the last one. I know you have a bunch of questions, so please feel free to ask in the comments down below. I'll get back to you just as soon as I can. But until then, we move on next week into the next chapter. So make sure to keep up with the homework. And again, just always ask if you have any questions. I will see you later. Until then, bye-bye.